So good afternoon, ladies and gentlemen, and welcome to the new seminar of MetaMAT. Today, it's my pleasure to introduce Cédric Bellis from the Laboratory of Mechanics and Acoustics of the CNRS in Marseille. And Cédric will talk about energetic and geometrical variational principle for computational homogenizations and applications.
All right, thank you very much. Thank you for this kind invitation. So I'm pleased to have this opportunity to present this work here. So I will talk about numerical methods for homogenization and some applications to the design of microstructures. So it's a joint work with two colleagues from the Laboratory of Mechanics and Acoustics, Pierre Suquet and Hervé Moulinec, and with a colleague Rémi Cornadia, who is now at Sorbonne University. Okay, so obviously we all know that virtually every solid material is heterogeneous, and often this includes several length scales. So this can be man-made composites, such as the examples on the left. So metallic composites, concrete. It can be also some natural materials, such as bones, which is a porous material, or polycrystals. And as you will see, also what I've coined as numerical materials. So in our work, we have to test our methods usually on some synthetic materials that we generate numerically to test our methods. And all of these are materials heterogeneous and possibly with some complex constitutive relation. So in this context, I'm interested in applying a static or a dynamical excitation to this type of medium, and asking what will be the effective macroscopic response to this kind of media. So the question I'm interested in is how to characterize and then optimize the effective static or dynamic response of heterogeneous media. So obviously we will talk about homogenization, and in particular to develop some models and simulation tools for forward multi-scale problems. And in this context, the problematics I'm interested in are first to have some numerically efficient methods to compute the effective or the homogenized properties, and to allow for application typically such as the design of architected microstructures or metamaterials. And the approaches that I will be using are the use of typically integral equations, asymptotic analysis, and optimization methods, as you will see. So the outline of my talk is the following. I will first discuss how to solve the forward problem, and in particular, I will introduce a periodic homogenization method. At least not introduce, but talk about it. And then to focus on some well-known energetic variational principle, and discuss what we can when we can build from that, and in particular some new variational principles that we have coined as geometric variational principles. And in my last part, I will describe some an application to the design of periodic microstructures. Okay, so let's start with the forward problem. So I've considered typically the heterogeneous elastic material, a linear elastic material. So we are in a situation where we have a microstructure, typically the one on the right here, where the geometry of the microstructure and the moduli of the elastic phases are given. So the elasticity tensor L is given, and we are interested in computing the stress and the strain. To do that, we need to solve the governing equations for these two fields. So in particular, the local field stress and strain solve the following boundary value problem, where we can prescribe the mean value of the strain. So we have the mean value of the strain, epsilon bar, which is something which we impose to the medium. So we have the following set of equations. The compatibility equation saying that the strain is the symmetric gradient of a displacement field. We have the constitutive relation, the equilibrium, and then the loading, which here takes the form of mean value of strain, which is defined as the integral over the unit cell characterizing the medium. This mean value is equal to the prescribed value of the mean strain, plus some boundary conditions, can be periodic or not. So once we have solved this boundary value problem, then to homogenize the medium, then we do some sort of post-processing. Typically, the effective properties are defined by applying computing the average of the strain, of the stress, and related it to the applied mean strain. And the linear operator that appears in this relation is the homogenized or the effective elasticity tensor that we were looking for. So in the first part of my talk, I will describe a way to solve this problem numerically efficiently. So first, we will be interested in an auxiliary problem where the heterogeneity, the medium heterogeneity, is transformed into a so-called polarization stress using the method introduced by Shelby in particular and Willis. The idea is to introduce a reference homogeneous medium, okay, that has to be chosen appropriately, and to rewrite the constitutive relation as sigma equals L naught epsilon plus tau, and this tau obviously encapsulates the heterogeneity. Okay, so tau is L minus L naught epsilon, so it's strictly equivalent. But now we will solve an auxiliary problem, which is a boundary value problem with a so-called polarization stress. So for the time being, we consider solving this problem in a reference medium which is homogeneous, okay? And tau for the time being is given. And because we are in a homogeneous medium here, we can use the Green's function of the homogeneous medium. And this boundary value problem, the solution of this boundary value problem is epsilon equals the loading, epsilon bar, minus the Green's operator applied to the polarization stress. Okay, so this operator gamma naught here is the so-called Green's operator for the reference medium. And we will see that it's a convolution operator. So let me say a word a bit more precisely on this Green's operator. The key point here is that in the case of periodic boundary condition, the Green's operator has a very convenient expression in the Fourier space. So I will take the Fourier transform in space of my boundary value problem. So I will introduce psi, the Fourier variable, which is a spatial frequency. So the Fourier transform of any function f is defined here. So f can be expanded as a Fourier series because we are in a periodic setting, and obviously the Fourier transform of the spatial derivatives are given as a multiplication in the Fourier space. So in this context, applying the Fourier transform to the boundary value problem, we obtain in a very straightforward manner that the Fourier transform of the Green's operator can be found analytically. And in the case of an elastic problem, this Fourier transform is this fourth order tensor. The key point here is that this Fourier transform is known analytically in the Fourier domain, whereas in the physical space, the Green's operator is some sort of a nasty operator that is strongly singular. In addition, the solution of the boundary value problem in the Fourier space is written here. So at the zero frequency, we have the imposed mean value. And at all non-zero frequency, the solution epsilon hat is given as a product of the Green's operator with the Fourier transform of the polarization tensor. And because we have this multiplication in the Fourier space, the Green's operator is indeed a convolution operator in the physical space. Okay, so here we have solved an auxiliary problem where we have made the heterogeneity disappear into a term called polarization stress. So now let's go back to the initial problem. So the problem where we wanted to solve the equilibrium for the equilibrium equation for the stress, where the stress is written as L naught epsilon plus what we have removed, so delta L epsilon, and as an imposed mean value for the stress, for the strain. So using the solution of the auxiliary problem, the solution to the initial problem now, we just have to replace what tau is here equal to, and we end up with a so-called an integral equation, which is called the Lippmann-Schwinger equation. So epsilon here is a solution to that equation, okay? So this is an integral equation because of this convolution product. So if I write this equation in full, you have a convolution of delta L epsilon with this kernel here that is constituted by the Green's function. But this is just a reformulation of the local problem. We have not solved yet the problem because epsilon, the solution, is outside the equation and also inside the integral operator. Okay, so the question now is how to solve this type of equation. Perhaps the most simplest idea we can think of is to use a fixed point scheme, okay, which obviously has some a convergence condition. Basically, just saying that we can initialize the strain, and to find the strain at the next iteration, just apply the integral operator to the previous iteration. Okay, so that's the first point, use this fixed point scheme, but we want to numerically avoid the computation of this convolution product, which was very costly. So the idea introduced by Pierre Suquet and Hervé Moulinet in the 90s is not to compute this convolution, but to do that using the forward and the inverse fast Fourier transform. Okay, so we'll compute the action of this integral operator in the Fourier space based on the fact that the Green's function in the Fourier space is known analytically and equal to the quantity I've given in the previous slide. Okay, so the algorithm goes like this. So we have a step of initialization, and then we will iterate. So knowing strain and stress at a given iteration, we will iterate both in the physical space and in the Fourier space. So knowing the stress at one iteration, we will apply the fast Fourier transform to go in the Fourier space. In the Fourier space, we will apply the Green's operator frequency by frequency by using a local multiplication at each frequency. We will fix the mean value at the frequency 0. Doing that, we'll end up with the strain at the next iteration, go back to the physical space using an inverse Weiss Fourier transform. And once we are in the physical space, then and only then we will apply the constitutive relation at each point. So we will go back and forth between physical space and Fourier space using forward and inverse FFTs. And the key point of this algorithm is that everything is local, in the sense that the constitutive equations is applied locally in the physical space, and the equilibrium and the compatibility conditions that are encapsulated into the action of the Green's operator are applied locally in the Fourier space. And doing that, we have a numerical complexity equal to this of the FFT. So typically n log n instead of n squared if we had to compute the convolution product. So what are the features of this FFT algorithm? So we have to realize that it's a meshless method in the sense that we compute the solution of the cell equation on images. So we have images of the microstructure, 2D or 3D with pixels or voxels. And by an image processing approach, we compute the solution to the local problem. So it's very easy to implement and to parallelize. And usually it's much faster than the finite element method for periodic boundary conditions. But it can also be extended to nonlinear behaviors. However, it has a number of limits. We cannot do local refinement because we have a uniform grid. Okay, there is a rate of convergence proportional to the contrast. So typically, the reference medium that we have introduced control the rate of convergence, but we have in any case, we can find a reference medium such that the algorithm is convergent. And we have some issues to deal with interfaces and discontinuities. However, despite all of this, the method has been successfully applied since the 90s and improved over the years. And I just want to show you a gallery of results that has been generated by my colleague Hervé Moulinec. So I show here some numerical results for some synthetic microstructures. So on the left, you have some images of 2D microstructures, and on the right, some fields that are computing using these image processing methods. And the constitutive relations that are used here are nonlinear, so elasto-viscoplastic or elastoplastic constitutive relation. So this is performed using 2D images, but it can be extended to 3D images. So on the right here, you see some images of a fiber reinforced composites in 3D or a polycrystal. And using this image processing approach, we compute local fields on this unit cell. And from that, we can compute the effective properties. So as a post-processing to this computation, since we know the local fields, then by doing some averaging operation, we can compute the effective tensor associated to this microstructure. Okay, so this is a numerically efficient method to compute the solution to unit cell problems. In the next part, I would like to relate that to a variational principle and to show you how we can extend the well-known energetic principle. So in fact, we have three equivalent formulation of the mechanical problem or of the elliptic problem that we are considering. So there is the local governing equation that we have just discussed, okay? Local governing equation posed in a cell, in a periodic cell describing the medium. There is the volume integral equation, which is the Lippmann-Schwinger equation we just discussed, okay? So a formulation that features the Green's tensor for the homogeneous reference. But we also know that there exists an energetic variational principle that states that the solution to these the two above formulation can be thought as the minimizer of an energy functional. So typically, we can introduce a functional that measures the energy, the mechanical energy in the unit cell. This functional is constructed from the constitutive equation. And if we minimize it in the right functional space, typically the space of kinematically admissible field, then we end up with the solution. And the minimum of that functional is related to the effective tensor. So in the next part, I would like to discuss in more extent this type of variational principle. So to do that, I would like to, in the next couple of slides, to introduce some functional background. Okay, so this has been known for a long time, typically in the works of Jean-Jacques Moreau or Graham Milton and Pierre Suquet as well. So to describe our fields, we will typically introduce two spaces, a strain space and a stress space, okay? These two spaces are some spaces of square integrable tensors. And we know that these two spaces are in correspondence owing to the principle of virtual work. Typically, if we take a field tau in the stress space and multiply it with a field in the strain space, this produces an energy, a mechanical energy, which can be seen as a duality product. So these two spaces are dual to one another. Next, I would like to introduce the uniform, the reference medium, a constant tensor L0, to define two scalar products in each of these two spaces. So on the left, I introduce L eta tildes. Okay, so this is some sort of a mechanical energy in the strain space. And I have the dual version using the inverse tensor of L0, okay? And these two quantities define some energetic scalar product in these two spaces. So we have now Hilbert spaces. Okay, next, I will identify some subspaces. So on the left, I will identify in my big space the subspace of uniform fields, so constant tensors, and the subspace of kinematically compatible strains. So typically the fields that are the gradient or the symmetric gradient of some displacement. On the right, likewise, I will introduce the subspace of uniform stress, okay, so constant stresses, and the subspace of statically compatible stresses. So typically, the fields that satisfy the equilibrium equation. And doing that, I have an orthogonal decomposition in each of these spaces. So on the left, I have the orthogonal decomposition between the subspace of kinematically admissible fields and the orthogonal part in blue. And on the right, the subspace of statically admissible field, and the orthogonal part in red. Okay. So in addition to this orthogonal decomposition, I can now introduce some orthogonal projectors. So typically, any field eta on the left can be decomposed by its mean, its part that is kinematically compatible, and one part which is in the orthogonal subspace. Likewise, on the right, I can say that any field, any tensor tau can be decomposed by its mean value, its part which is statically admissible, and its part which is orthogonal to the subspace. So I have two orthogonal decompositions. Lastly, I can remind myself about the Hill lemma. So what does the Hill lemma says? It says that if I take any fields E which is kinematically admissible, then these fields produces zero energy if we compute it against a field S which is statically admissible. What it means geometrically is that the subspace of statically admissible field, S naught, statically admissible at zero, is a dual to the orthogonal subspace of kinematically admissible field. And likewise, if I take any field S which is statically admissible, then it produces zero energy for any field E which is kinematically admissible. In other words, geometrically, it means that what we must keep in mind as a mental image is that the subspace of kinematically admissible field is the dual to the orthogonal subspace to statically admissible fields. Okay, so this gives me a functional and geometric description of the functional space that I want to use to solve my problem. So how to use that now? If I go back to the local governing equations and keeping in mind the decomposition I've just described, then we can rewrite the governing equation into a condensed form, saying that the strain that I am looking for belongs to the kinematically admissible parts. The stress is statically admissible, so it's in the blue subspace here. And the relation between the two is given in terms of the constitutive relation. So now in this setting, what is the role of the Green's operator? How we can construct the Green's operator for a given reference medium? In fact, what we have is that the Green's operator applied to any tau produces a field E star, which is kinematically admissible, and such that this quantity S here, where I have the field E star against the reference medium minus this polarization stress, is a statically admissible field. Okay, so the Green's operator produces a field that satisfies these conditions. And this is a strain-based Green's operator. We have the dual stress-based Green's operator. The key point to underline here is that, in fact, given the definition of the Green's operator, then the orthogonal decomposition in the strain space can be expressed in terms of the Green's operator. So again, saying that any field eta can be decomposed by its mean value, its parts in the kinematically admissible subspace and an orthogonal part, then the orthogonal projectors can be expressed in terms of Green's operator. And that's the key point here. Okay, so now, what can we do with that? So let's consider the minimum energy principle. So we have the energy functional. So J of E star is the mechanical energy for a given field E star, given that the mean value is epsilon bar. Then the minimization principle we have is to try to minimize this mechanical energy into the subspace of kinematically admissible fields. And the minimum value is related and is given by the effective tensor. So because we are doing a minimization problem, we can try to compute the gradient of that functional. So we'll compute the gradient of the energy into the strain space endowed with the energetic scalar product. So we'll compute the gradient in this space and use the orthogonal decomposition that is expressed, as we have seen, using the Green's operator. So the computation of the gradient of that functional leads to this expression of the gradient here. So the gradient of J is given by the Green's operator applied to this quantity here. And this has been observed in the relatively recently by these authors. The key point here is that the optimality condition, so the gradient of J equals 0, is strictly equivalent to the volume integral equation. You can, it's a bit technical. It uses a few properties of the Green's operator, but this optimality condition is exactly the Lippmann-Schwinger equation that we have seen in the first part. So with this observation at hand, we can revisit the very classical fixed point algorithm as in fact a gradient descent algorithm. And what we can observe is that this fixed point algorithm is a gradient descent algorithm where we try to minimize the mechanical energy. And this is a gradient descent algorithm with a fixed step. So this observation has led to the use of much more efficient, meaning accelerated optimization algorithm to solve the cell problems. Okay, so now we have these three equivalent formulation of the forward problem: the local governing equations, the volume integral equation, and the energetic variational principle. In this context, we can ask ourselves how to compute the effective response using some alternative variational principle where we can relax some of the equation of the problem. Typically, in the next couple of slides, I will describe you some alternative variational principle where first we will use a single field principle where we'll try to minimize a measure of the static admissibility, and then use a fully unconstrained problem for two fields, basically saying that we will find the solution to the unit cell problem by minimizing some discrepancy with respect to the compatibility condition, the constitutive relation, and the equilibrium. And in other words, we will try to compute the solution of the problem while relaxing all of the equation of the problem and explore the entire space of possible solutions. So let me describe that in the next couple of slides. So first, let's consider a single field formulation. A very simple idea that we can have is that rather than minimizing the energy functional J, we can minimize the norm of its gradient. Okay, because if the norm of its gradient is minimized to 0, then we have reached the optimality conditions. And I recall that the norm of the gradients, or that the gradient itself is given by the expression we have found in terms of the Green's tensor. So let's recall that we can decompose the space of stresses between uniform fields and statically compatible stresses that satisfy the equilibrium equation. We have the orthogonal decomposition between the statically admissible space, subspace, and the orthogonal part. Then an orthogonal decomposition, an orthogonal projection, sorry, written in terms of the Green's tensor. Well, in this context, we can recognize that the cos functional n introduced above here is exactly the norm of the projection of the quantity here into the orthogonal subspace S. Okay, so in other words, what it means that the functional n introduced above here is some sort of a measure of the static admissibility. Okay, so we measure the discrepancy to the equilibrium. And what is interesting here is that the stationary value of that functional is 0, whereas the stationary value of the energy is not known a priori. And we can relatively easily compute the gradient of this new functional. Okay, so this is a first reformulation using a single field variational principle into a constrained problem. Okay, so we minimize the discrepancy to the equilibrium over the set of kinematically admissible fields. But what about a fully relaxed formulation? So for the time being, let me discuss a two-field geometric variational principle. My objective here is to now relax all of the equations of the problem. So I replace the set of 3 equations describing the problem. I fully relax them in the geometric setting that I have just discussed before. So the idea is to look for the solution sigma epsilon, so stress and strain, by minimizing this two-field functional, which is constituted by 3 parts. I have 2 parts which are some measure of the static admissibility using the projector into the appropriate subspace. So this part is the same than before. I have a new part which is the dual, which is the measure of the kinematic admissibility. And in between, I have a measure of the material admissibility, which is a quantity that measures the error in constitutive relation. Okay, so the error to the material law. So it's written here in terms in the linear case, but it can be extended to in the non-linear case. Again, the optimality, the stationary value of this functional is 0, and we can compute the gradient of that functional relatively easily. And we can check that the minimization of that functional is compatible with the usual energy-based minimization principle. Okay, so at the end, so what do we have? We have a number of variational principles for functionals that are either energy-based or geometry-based. And for all of these functional, we know how to compute the gradient. So we can implement some gradient descent algorithm, let's say optimal step, a conjugate gradient, quasi-Newton. And we will perform some iterative construction of the solution in a setting where we use the FFT ID. So typically, every time we have to compute the application of the Green's tensor, which are some projectors, we do that by applying Fourier transform and inverse Fourier transform and the Green's operator known analytically in the Fourier space. So I show you here a representation of the iterations. Okay, so I put in the space where I measure the error with respect to all of 3 equations of the problem. So the error in constitutive relation, the error in kinematic admissibility, and the error in static admissibility. I represent the iterations of the solution towards the exact solution at the origin. So these are 3 representations of some well-known methods, where every time there is 2 or 1 equation which is enforced into the iteration. So either the kinematic admissibility or the constitutive relation that they are enforced and supposed to be known exactly. With the new formulation we have proposed, now we are exploring the solution into the entire space. Okay, so we minimize the geometric functional in the entire space. So it's a non-constrained problem that can be solved using, let's say, a conjugated gradient. So we converge to the solution, but while having relaxed all of the equation of the problem. So doing that, we can introduce very easily some uncertainty in the model, or replace the constitutive relation by some data points, some experimental data points characterizing the material. But we can still converge to the solution of the problem. So now we have a set of numerical methods to compute the solution of a periodic problem. And I will show you in the next part how to use them in an application where we want to do a design and optimization of a periodic microstructure. So the context is this of dynamical homogenization. So typically I have scalar waves into a medium characterized by 2 constitutive parameters. So my constitutive parameters are mass density and shear modulus. Okay. And I place myself into the long wavelength regime. So the characteristic length scale of the microstructure is much smaller than the wavelengths. And in this context, I can perform a 2-scale asymptotic expansion of the solution UL, okay, solution to the wave equation. So the solution to the wave equation can be expanded as the macroscopic field, plus some higher order oscillatory correctors, okay, which are given in terms of cell function, okay, so P1, P2, and etc. are some solution of a cell problem written into a representative unit cell. And these cells problems are static problems that are exactly the ones that I've described the solution in the previous two parts. Okay. All right, so doing this 2-scale asymptotic expansion up to the 2nd order, we obtain using formal asymptotic expansion an enriched homogenized wave equation for the mean field. So the mean field capital U solves this equation here, where at the order 0, you recognize the standard homogenized wave equation. But because we push to the 2nd order, the asymptotic expansion, we have some higher order derivatives that govern this the equation for the mean field. So in that equation, I have a set of 4 parameters, which are effective dynamical parameters. And the definition of these parameters, so the effective mass modulus and shear modulus at the 0 order or 2nd order, are written in terms of these cell functions. Okay, so to compute the effective parameter, the homogenized parameter, we need to solve a number of cell problems. Okay, so now what are the key features of this effective model? To characterize this model, we can use a plane wave analysis, okay, to typical of the Floquet-Bloch analysis to obtain the dispersion relation. And what we obtain is that, for example, the phase velocity at a given wave number k and for a direction, a plane wave direction theta, so c is omega over k, this can be expanded as the second order consistently with the asymptotic analysis. So we have a first order term, or a term at the order 0, sorry, which is some sort of a low frequency limit velocity, and a second order term, which is accountable for a dispersion, a dispersive behavior of the effective model we have obtained. And these two quantities depends on the effective parameters. Okay, so now what we can ask ourselves is to finally how to design the microstructure to achieve some target effective properties. So for the remainder of the talk, I will consider a topological optimization problem where we will try to determine the microstructure, so the distribution of mass density and shear modulus that achieves the minimization of a given functional of the effective parameters. And if we do that, we have a chain of dependencies. Starting from the description of the microstructure, we then have to compute the cell functions. From this cell function, we obtain the effective parameters, which leads us to the macroscopic observables that I have described above. So the low frequency limit velocity and the second order dispersion term. And based on these two observables, I can construct and evaluate a given cost functional f. So as an example of a cost functional, we can typically try to minimize the dispersion in a direction theta minus and maximize it in the direction theta plus. Okay, so we have a minimization problem for the effective parameters. So how to solve this minimization problem? So the last ingredient to be used here is to evaluate the how a change in the microstructure affects the chosen cost functional. So what we want to do is to try to modify, to iterate on the unit cell on the microstructure by doing some small perturbation and to see whether that increase or decrease the cost functional considered. So to do that, basically, we will try to compute the gradient of the cost functional with respect to a topological perturbation of the unit cell. So I consider my unit cell with mass density and shear modulus, and then introduce a small perturbation at a given point. And the idea is to compute an asymptotic expansion of the cost functional. So expand the cost functional at the first order and to identify the first order term here, which is the so-called topological derivative. So the topological derivative quantifies how much an infinitesimal perturbation of the unit cell affects the cost functional. So in the case of the effective model, and of course using the chain rule, to compute the topological derivative of the cost functional, we have to compute the topological derivative of the effective parameter themselves. Okay, and for the model considered, this has been done by in a previous work by Marc Bonnet, Rémi Cornaggia, and Boyan Guzina. So the key point here is that to compute the topological derivative of the effective parameters, we have to compute 12 scalar static cell problems. Okay, so scalar cell problems in static, which are of this type. And these are the type of problems for which the method I have described in the first two parts are dedicated to. Okay, so the numerical strategies are typically use finite elements or the FFT-based method that we've discussed earlier. Okay, so now we have a way to compute the gradient of the cost functional, and we have a numerically efficient way to do that. How to update the microstructure? So let me give you an example. So typically, considering this simple cost functional where we try to minimize the dispersion at the angle 0 and maximize it at pi/2. Then for a two-phase unit cell with a black and white phase with some known properties, well, we can either use a pixel by pixel algorithm. So typically by starting with a random microstructure, we will swipe phases at the points where the derivative is maximum and minimal. And then in a number of iterations, we will converge to the expected laminated structure. So this involves 241 iterations. And at each of these iterations, you need to compute 12 scalar cells problem. So this is relatively costly, so that you need to have a numerically efficient method. Alternatively, we can also use some level set algorithm. So using a method that's been proposed earlier, the idea is that at one iteration, the topological derivative defines a level set function that itself defines the boundary between the black and the white phase. Okay, and doing that using these methods, it's much more efficient, and in only a few iterations we converge to the same results. All right, so now that we have this method, we can play with it. So let's consider a slightly more complicated example where you would try to minimize the dispersion at plus or minus pi/4 and maximize it at 0 or pi/2. We start from a microstructure, a random microstructure with a constraint, with a symmetry constraint. And after a number of iterations, we end up with this microstructure that optimize the cost functional considered. Okay, so we have a tool, and now we can play with it to solve various optimization problems. But we can also use that tool to do some inversion. So typically to reconstruct, to identify a microstructures from some macroscopic dynamical measurements. So let's say that we have some macroscopic dynamical observables. We can try to minimize the misfits between these observables. So just let me show you an example. We considered a chessboard for which we generated some data, synthetic data using Floquet-Bloch analysis. And then we try to fit this data. So we try to fit the phase velocity and the dispersion for a number of wave number. And after a few iterations using this the proposed methodology, we converge to this identified microstructure. So given that we've started from a chessboard. Okay, so a reconstruction of a microstructure from dynamical macroscopic observables. All right, so let me conclude. I wanted to discuss and to present to you some numerical and theoretical tools dedicated to computational homogenization, and so the computation of cell problems in the periodic setting. So we have discussed some novel geometric variational principles. one interest of this new type of variational principles is that we have relaxed all of the equations of the problem, so we have much more flexibility to play with the constitutive law. We can typically use some data-driven approaches, work with some, integrate some experimental data directly into the forward solver. As a side remark, we are also working on adaptive computations, which is relatively challenging for these FFT-based methods. And then, so I've presented to you some numerical methods to solve these periodic problems and optimization problems. We are currently working on extending the optimization approach to the computation of microstructured interfaces with Marie Touboul and Rémi Cornadja. So we want to optimize microstructured interfaces that achieve some effective dynamical properties. And we are also working on the FFT-based computations of dispersion diagrams in acoustics and elasticity. So this is a methodology that has been known for a long time in the photonic community, but I don't think it is known as well in the elastic and acoustic community. The idea is to have a fully integrated approach, starting from the characterization of a periodic microstructure to the computation of the effective parameters, and then to the optimization of these microstructures. And with that, I would like to thank you for your attention, and I'll be pleased to answer any questions.
Thank you very much, Cédric, for the nice talk. We have time for questions, so just unmute yourself and you can ask the question. Alternatively, if you don't have a microphone, you can write the question in the chat.